This video includes a demonstration of the throughput measurement test added as of OpenCPI's 2.1.0 release candidate 1 release. These test artifacts are located in the project's assets, and it consists of two new components, the test sink and the test source, as well as assemblies, test sink assembly and test source assembly. So the components each have the RCC worker and an HDL worker so that they can be executed on either the ARM or the fabric. The FPGA requires assemblies, and the workers are included in those assemblies. In the test source assembly, since it's generating the data, it's generating this at 32 bits at a time. There's an additional property that you can use to set the rate at which it generates the data, and that's called the clock divisor, and that divides the control clock, the 100 megahertz clock, depending on what that value is. In the applications directory under project's assets is the run mode script, and that's what we'll be demonstrating today. So just some prerequisites before you can run this script. Download and install OpenCPI, starting from the release candidate 1 and above, and then installing the target platform you want to run these scripts. In this video, I'll be using the E310, and then build the assemblies for the target platform. So there's the test sink assembly and the test source assembly. To run it, you'll be using server mode, also known as the OCPI remote, and from the development host, make sure that your OCPI library path exports core and assets. So I'm in my OpenCPI tree, and I'm going to initiate OCPI remote. I'm going to begin with exporting the path. Assets, artifacts, and core artifacts. And OCPI server addresses. I'm going to point it to my E310. And it's the IP address and the port. I think it's already loaded. We could check that. OCPI remote status. I always forget to get my environment variables. Yeah, it's already running. So in applications, there's a script called run mode. First argument is the mode. So there's 3 different modes, 0, 1, and 2. The 0 and 1 have been implemented. 0 basically means no cache coherency modifications, running it just the way it was before. 1 is adding software side cache coherency, and 2 would be hardware enabled, which moves the data plane from the AXI high performance ports to the ACP port available on the Zinc, but that is still being worked on at the moment. The second argument is the platform you want the source to be executed on, and then the second one is where you want the sink to be. So for this first demonstration, I'm going to use the E310. I want to generate data from the E310 and receive it on the ARM platform. So what this is modifying in the test cases is the number of buffers. You can see here, starting from the E310, 2 buffers. From the HDL side, it's always going to be 2 buffers, but from the software platform side, we can increase that buffer and the buffer size. And this is the output that we see. So the buffer size, and then whether the CPU touches the data, which is no touch, is 0, meaning it's going to touch it, and not touching it, it's set to true. And this is the throughput measurements that we're reading based on these different settings that you could change at runtime. So without touching the data, we can see that we're getting, a theoretical 400 megabytes per second, close to theoretical for the zinc. But when we touch the data, it greatly diminishes. So at a 32 megabytes per second, that would be considered 8 megasamples per second, because there are 4 bytes per sample. So setting the software platform to use 2 buffers with a buffer size of 16 seems to get us there. So it tests both from the E310 to the ARM, and then it does the other direction as well, from the ARM to the E310. So now let's try going from the E310 all the way to our development host. In our case is Ubuntu 18.04. And let's change the mode from 0 to 1. So we're going to enable some of the DMA caching features that we've added. So again, it's modifying the number of buffers on the Ubuntu side and the buffer size. And since we're going from the FPGA fabric all the way to development host, it does have to touch the ARM, so the CPU gets used. So the difference between no touch and touch, well, no touch false and no touch true is negligible. So from the FPGA to the Ubuntu, we're getting solid above 8 megasamples per second, and now it's testing it from Ubuntu to the E310. So from the ARM to the fabric, there is limitations of it can only be the receiver on the SDP receive can only be 2 buffers on the E310. So we can see here that using Ubuntu E310, 2 buffers of 16K gets us to the 8 megasamples per second.